Hello, everyone, and welcome to a new final project presentation ceremony. So today we have one presentation, just one, which is going to start right now in a moment, but it's a very interesting one. It's a brand new project that we have added to the masterclass. And it's going to combine a bit of everything, a bit of manipulation, perception, even AI. So yeah, I don't want to take much more time, and I prefer that our student Roberto directly presents and introduces his project properly. So let's say hello to Roberto. There we can see you. Roberto, can you hear me? Yeah, 1 second, because I'm not sure if people is able to hear you. Let me check there. Let me ask the people there in the chat. So, were you able to hear Roberto? I mean, I can hear you properly, but no audio. Okay, yeah. So it seems like there's some kind of issue with the audio. Let me check that real quick.
Devo da calúcia.
Hello, hello. Let
Hello.
me verify if at least they can hear me, because I'm not even sure that they could hear me. So can you guys hear me? Yes.
I have somebody in the room on the live stream and I could hear you through their live stream before, but I don't think I could hear myself.
Yeah, I think that they are telling me that they can hear you now. So can you hear
Okay.
Roberto now? Can you confirm that?
Hello, guys. Can you hear me?
Yes, now good. Okay, so I think we are good.
Okay. So, hello, guys. Thank you
Hello.
so much for joining us. Really glad to be here to share my final project with you guys in the Ross Masterclass. I'm a mechanical engineering student that just graduated, and I have a passion for robotics. So this is why I joined the masterclass. And yeah, this is my final project. It's Tic-Tac-Toe. It's a robot arm, the Piper from Agile X, that is capable of playing tic-tac-toe with a human player automatically using perception with OpenCV and its own AI game engine to be able to decide which move is best to compete against the player. And in the current setup, we have the robot arm, an electronic board with a little stencil, a little stylus in a foam block to allow the robot to draw anywhere on the board. And for perception, we have a camera, in this case, an Intel RealSense camera. And all of this can be controlled through a web-based application, or it can be fully autonomous. So this is the overall layout of the ROS nodes. I'm going to start going through this from the top left, starting with the Intel RealSense camera, which feeds the board processor, the necessary RGB data. And board processor has OpenCV, which is capable of taking this data and processing it into a board state. So it goes through and computes the state of each of the cells on the board. It publishes this on a topic board state, and at the same time, it also publishes some final debug images that can be then given to the web video server to be displayed on the web interface. From there, the board state is also transmitted to the web interface through the Rossbridge WebSocket. And this updates in real time the display on the left-hand side with the current board state. At the same time, this board state topic feeds into the Move Manager, which is the manager of robot moves and also human moves. So once Move Manager receives a board state, it uses that information along with the requested move to then request the trajectory server to plan and execute a trajectory. And from there, the trajectory server then calls the move group, which is powered by MoveIt2 library, to plan and execute this Cartesian trajectory. And this move group can either be run in Gazebo or on the real robot with a very similar setup. And this enables us to test very, very seamlessly between the two environments. From the web dashboard, on the left-hand side, we have buttons that the human operator can press to send a play move request, which feeds into the Move Manager. Or the game can be set into automatic mode, which basically means that the robot continuously monitors the board state and waits for the human to draw on the board. And once it detects a change in the board state, it can then respond and produce its own move based off of the algorithm that's running under the hood. And just a brief description of the algorithm, it's based off the min-max reward algorithm. It basically calculates several moves ahead until it completely fills the board. So it's a recursive algorithm, and it summarizes the total score of the human versus the robot at the end of the calculated match. And it tries to maximize the score for the robot in order to compete with the human. So moving on from here, the most important part of this project and the part that took the most time to perfect was the image processing pipeline. And this was done completely in OpenCV. We first detect the board contour itself. And this is the first major step, board detection. Second step, once we get our board contour and can apply a perspective transform, we can then segment this image to get each of the individual cells. And once we have the cells, we can then move on to the third step, which is detecting the symbols in each of the cells, which is arguably the most challenging part of this process. So first of all, board detection, we receive the image topic and convert it to the proper format for computer vision OpenCV bridge. And then we take this RGB image and convert it to the HSV color space, the hue, saturation, and vibrancy. This allows us to isolate the colors, to be able to mask and filter out everything except for the very bright turquoise outline. And we want to use this to then find the contours using OpenCV. And we select the innermost contour, which happens to be the area for the drawing space on the board. And we approximate the corner points. Once we have obtained these corner points, we can apply the appropriate perspective transform. This allows us to take our off-angle view of the board itself and warp it in a way that we perceive it from above. And everything is in proportion now. Then we crop it slightly just to remove any residual border. Next step is to be able to get the edges of the actual things drawn on the board. We need to first apply a Gaussian blur. This removes any noise in the image. Without this, you would see a lot of dots all over this black and white image on the second image. And then we apply an adaptive threshold. This adaptive thresholds, instead of having a static threshold, which we did for the first step of isolating the board contour, this adaptive threshold is more robust to different lighting conditions. And you can see the color of the lines on the board slightly changes from the left-hand side to the right. That's due to where the lighting source is positioned. So using this adaptive threshold, we eliminate any errors in detecting edges. And then the next step, the third image, we detect all the lines using a hue transform algorithm in OpenCV. And we filter out the vertical and horizontal lines. And from these vertical and horizontal lines, we can find the edge boundaries for each of our cells. And we can finally segment the image into 9 cells. And then from there, the most challenging part is the symbol detection. So initially, I did this symbol detection for the circles using the commonly used hue circle transform in OpenCV. However, this is really specific and expects nearly perfect circles all the time. So if a human player was to draw a circle that was a little bit misformed and not perfectly round, it would fail to detect it. So I had to come up with something a little bit more robust for this that can account for these different types of circles. And this flowchart here is the logic behind detecting an X versus an O. So starting from the top, we detect lines for a candidate X, and we see if they cross at about a 45-degree angle. And we leave a bit of a range between 30 and 60 to be sure we capture the most amount of X's. And we accept it if we find an intersecting line. And if not, then we move on to detecting contours, which you can see on the left. The contours are in green and red, and the red ones are the longest contours that are detected. From there, we use the area moments of inertia to approximate the center of this contour loop so that we can then calculate several metrics, which we need to determine whether this contour is actually a circle or if it's something erroneous, like the X that you can see in the middle column on the top. So if we go around the contour loop, we calculate the average radius, and we also calculate the standard deviation, the distance from that center point, and we calculate the standard deviation of that distance versus the actual average radius. And if this is a very large deviation, then we found something erroneous. It's not a circle, which means it's more likely an X. And we can retry to see if it's an X or if it's actually empty. And if we did find something that's suitable, then we can accept it as a circle. And this method produced much better results than just using the circle transform. And to improve it even more, I also use this OpenCV transform, the morphological transform. This allows us to reduce a lot of the noise and the gaps in these circles. And by adjusting the kernel size, we can inflate the circle contour and erode in order to get rid of all these gaps that are producing many individual contours. We want to increase the kernel size to be able to combine all these contours into one large loop, which will allow us to more robustly detect circles. So you can see on the top, we only have a kernel size of 2. We have a lot of gaps left over, but on the bottom, after increasing it some more, we get a more robust detection. And with OpenCV, we also open the door to processing different types of images. So in this case, the construct logo, it's a very good candidate for image processing and getting contours. We first need to skeletonize and find the contours. And then you can set a certain step size and generate points along these contours to then feed into Move It to be able to draw it on the board. And if we have time later in the live stream, we can try to demonstrate this. So thank you very much. This is all for the presentation, and now we can move on to the live demo.
All right. So thank you, Roberto, for the presentation. This drawing thing, just to mention that it's an extra, okay, not something that is included in the project, but something that Roberto decided to do as something extra. Hopefully we will have some time later to have a look. And yeah, so are you connected to the lab, Roberto?
Right now, I have to check. I don't think I am, but I will try to connect right now.
Yeah, there. So I have my colleague Rodrigo, who is there in the setup. There's a little bit of delay in the YouTube stream from what I can see, so it's going to take a bit of time. There's going to be like a bit of delay for the game, but shouldn't be a big issue. Also, let me remind, meanwhile, to anybody here in the stream, I can see there is quite some people here. So in case that you have any questions about the project, about what Roberto has been explaining, so you can share them here, and at the end we will have a brief Q&A section to make some questions to Roberto. We cannot see your screen, Roberto.
I
By the
think
way.
we may have to restart the lab service,
Okay, so
having some issues connecting.
yeah, let me ask Rodrigo, sorry, to restart the lab to make sure that we can connect properly.
Okay.
So it might take a few seconds for him to hear it. So we cannot see your screen, Roberto. If you could share.
Yes, I'll share one more time. Yes.
I'm not getting it here. Okay, there it's coming. Okay, so did it connect properly now?
No, I think it may have skipped over the steps. May have to be restarted.
Okay, yeah, maybe it was just restarting. Then okay, I just received the confirmation from Rodrigo that it has been done. So yeah,
Okay.
just try to disconnect and reconnect again.
Yes.
Okay, so let's try Ross to. Let's see if we can properly see the topics now.
Almost there.
It's just taking a lot of time to load the terminal, which is a bit
I may
strange.
have to restart the ROS check entirely. That may be the
Maybe we
issue.
can try that, yeah.
Yeah. Okay. Yeah, I think we should. Things from live demos. Yeah.
Don't worry, we will connect. Okay. You are like already connected, apparently.
Yeah, I'm not sure if it was supposed to be connected still, but let's see. Now it's loading the
Yeah,
terminal.
let's have a look, and if not, just disconnect. We disconnect and reconnect. Okay. Yeah, it doesn't look like. So let's disconnect and reconnect, yeah?
Okay.
Okay.
Yeah, perfect. Now it's going through all the steps.
Yeah.
Okay. Let's confirm. Yes. Okay.
Okay, great. Okay. So we are launching the systems, right?
Yes. And now I can get the web page address. Okay. It is started.
Okay. So this is
Okay.
the web interface to control everything, right?
Yes. Yeah. So here on the center is the live camera stream from the Intel RealSense. On the left is the controls for the board. You'll see a grid very soon with all the buttons necessary for the controls. And on the right side is the image detection. And we can start a game. We can select different symbols for player and robot, and we can set it to autonomous or manual control for the robot. So for this first game, I think we can leave it as is and start the game with the robot being the circle.
Mm-hmm.
So I'll go ahead and start. It's going to start by drawing the grid on the board. Once it does that, it's going to go back to the home position and allow the camera to detect the grid. Okay, there we go. The grid's detected. And now Rodrigo should be able to make the first move.
Okay, so it's the
Anywhere.
player's turn. Let's see.
Yes.
Yeah, it's going to have a bit of delay, but he will listen it eventually, and then he will draw. So, and the player
What do you-
is X's, right?
Yes.
Okay. So Rodrigo should, yeah, draw an X wherever he wants. Okay, I think he's going
Okay.
there. Yeah.
There we
he
go.
goes. Okay.
That's the first X.
Okay.
And now the robot responds with the automatic move. And we can continue on with the game.
Okay. This is a close game so far.
Yeah.
Let's see what Rodrigo decides. Okay.
It's pretty tough to beat this robot.
Ooh. It seems like this is going to end in a draw.
Yeah.
Yeah, it's a draw. Okay. Interesting, interesting. Okay.
Yeah.
So maybe we can try the other way around, Roberto.
Yeah.
To
Yeah, we should.
Let Rodrigo draw the O's now.
I think first maybe we should refresh the web page or maybe restart because I'm not
Yeah.
receiving all the images. I'm just receiving one.
Okay.
So I'm gonna go ahead and end the game right here. That's gonna go ahead and erase the board. And now I'm gonna go ahead and just restart.
Okay.
Okay. And now we can switch the players.
Yeah. So now
And
the robot goes with the X's and Rodrigo goes with the O's. Okay.
yes. And since the robot is the X, it should be playing the first move.
Okay. So now the robot will be playing the first move and Rodrigo the second move.
Here we go. Now we have the images.
Okay, so Rodrigo's turn to draw one O. There we go.
Yeah, you can see even really
Yeah,
weird looking O's can be detected well enough.
it looks like Rodrigo is about to lose, I think.
Oh no.
Okay.
Okay.
Yeah, great. Okay. Yeah, so the
There we
robot
go.
won this one. Yeah, so thanks Rodrigo for your collaboration. He's finishing there. Yeah.
Another circle.
He's thinking it's a circle. Yeah, that's interesting. Yeah. Okay. All right. Yeah. So very cool also to see all the detections being updated live here with the web application, right? So so yeah, I don't know if you want to show something else, Roberto. Maybe we can try the drawing demo, or we have some time still, I would say.
Yeah, I think we can. It may just take a few minutes to set it up, but we definitely can try.
I think it's worth at least giving it a try. It's a cool demo, so
And if people want to ask questions or anything in the meantime,
yes.
we could always do that.
Okay, so yeah. So in case that you guys have any questions, well, I can see already some questions here in the chat. There's a lot. Let me try to go over them to see. Ah, not a question, a comment that might be interesting. Here, Dimitri, for example, who is also a fellow masterclass student, he was saying, wonder if small CNN, so convolutional neural networks for EXO, would be better than geometrical analysis of figures. Could be. That would be an interesting approach also. Here we have another question, for example, from this project is only for 3x3 matrix, or can it handle also, like, for example, 5x5 or more sizes?
Right now, it's only for 3x3. That's whenever that image processor is running, it's always expecting there to be exactly 9 cells. So if it sees anything different, it's going to throw an error and say that the detection hasn't worked. But I tried to make it so that those detection cells don't have to be strictly in the same place. If the lines are drawn by a human player, or if they're not drawn completely straight, the cells can try to adjust to account for that. But it always wants to expect for 9 cells for the tic-tac-toe game.
Here's an interesting one, because this is something that you have not mentioned, but we have talked about it in this project. So, for example, here, Dimitri also is asking, is there physical detection that the arm touches the board, or is that pre-configured? You can properly answer that question.
So right now, there's no physical detection of the board. Right now, it's just a fixed Z height off the table. But I actually designed something. I was pressed for time and I wasn't able to edit the presentation, but I did design a little module that could be added later that has a little force sensor and a small Arduino Nano. And with that, you could actually measure the force in real time. You just simply read off the serial of the Arduino through USB, and you can write that serial into a ROS topic, and that can measure the force in real time. So with that little module, you could actually move the pen down to the board and measure in real time when it touches anything on the board and be able to calibrate it that way.
Yeah, so that is something that we were thinking of adding to the current setup, but yeah, because of time limitations, we didn't. But yeah, it's something that for sure we are going to add to the project, so that you can have also that feedback to know where the board exactly is. Is it on the pen or where the sensor with Arduino? So no, right now it's not there. Right now the setup is just a pen It's just a basic pen, so with nothing else. Okay, then by trial and by testing, so finally we got the proper distance, and then we use that one. So currently there is no sensor, but that is something that we would like to add. And Roberto actually designed a very cool prototype for
This
that.
is a little prototype. I had it in my drawer just now.
Wait,
It's
give me a second because they are not seeing it. Let me switch.
Yeah.
Wait, how can I? Let me switch the camera to the other one. How can I do this? Give me a second. Here. Pin. Okay, yeah. Now they are seeing
Yeah,
it.
good. Okay.
Yeah.
So this is a little stylus pen for my tablet, and I just designed something really small. It's has a little spring inside, so when I press down, it moves slightly. And on the end of that spring is a little force sensor that comes out of here. And I soldered some wires to it directly to an Arduino Nano. And from this force sensor, it's basically just like a resistor. So you just measure it with any like analog signal from the Arduino, and you can output a digital value from that straight through the USB. So once you connect this to a computer, you just read off of the USB the serial output, and you can write your own small ROS node and read from serial and output to a topic in real time. So it's a very simple way of adding little sensors to your robots just by using an Arduino Nano or any other Arduino for that matter.
Okay, so let me remove the pin now. Switch to, okay. So do we have it ready for testing, Roberto?
Yes, almost, yeah.
Okay. So meanwhile, let me make you a question also. So you mentioned that the final version is pretty. You can switch pretty much smoothly between simulation mode and real mode, right? But initially, I assume that you started working and testing in simulation everything. So when you switch it to the real world environment, what is the thing that you had to it differed more from the simulation environment?
So in the real environment,
Hmm.
compared to simulation, everything's not perfect. So when you draw like a certain trajectory in simulation from point to point, you plan a Cartesian trajectory from one point to another, it'll be perfectly straight in Gazebo. But once you actually draw that on the real board, you'll see that it has a little bit of a curve, especially when the arm is swinging at its base in this like in the up and down direction on the real board, you see a bit of a curve. It's not perfectly straight. And that's most likely because when it's pressing down with the pencil on the board, there's a lot of friction on the end of it. So when it's swinging that arm across, it needs to account for that friction by pushing the pen in and out at the same time that it's swinging. And it produces like a bit of a curve. It's not a perfect straight line.
Mhm.
So I think probably a solution to that would actually be this force sensor. If you can add this force sensor and be able to constantly adjust the height of your pen to keep the force a constant, then that might actually help to produce more straight lines rather than curves.
Mhm. Okay, so what do we have here?
So I just launched the move group,
Mhm.
and now I also actually need to launch one more thing. I need to launch the trajectory executor,
Mhm.
the same one that was used for the Tic-Tac-Toe project. And that will basically take the set of points that I'll feed it as a contour and output it'll plan and it'll execute that trajectory and hand it off to move it to execute the trajectory. So just gonna launch that really quick. I need to remember the exact name. Okay, that's the trajectory server.
Mhm.
This is the move group. And now we should be able to launch the contour planner, which processes the image and outputs a set of points. And I have a set of parameters that I need to give it.
Mhm.
So I have an image folder. Wait, I'm looking in the wrong place. Yes, I have a set of images here. So we can try, oops, we can try this one first, which is just a smiley face. It's a pretty easy one. And then I took the construct logo and I cropped it a little bit. And then from there, we should be able to output something that looks like this and generate some points from it, hopefully.
Okay, so let's see what we can
So we
get.
need to give some Ross args. I should have made a launch file for this, but I was a little bit pressed for time. Start with a smiley. And I think we can just do that.
Let's see.
Okay, so it created all the contours. I think it outputted an image. Let's see. Nope, that is the wrong one. So yeah, it did output an image and the points, but it did not execute it.
Hmm.
Okay. I think it's using the old trajectory server. That's,
Hmm.
sorry, just a second. I'm just going to rebuild the package just to be sure and source it. And rerun it. Okay. Everything's ready. Let's try it one more time. Okay. And I wish I could see
You
let's
should
see,
have
can I see
it
it from here?
there. Yeah.
Yes, there we go.
Okay,
Perfect.
it's doing it.
So now it's drawing the smile, the mouth. And with the way that I processed the images, it generated two contours for each of the lines in the image. So it's going to repeat some things
Mhm.
twice, or it's going to repeat everything twice. This one is pretty short. It should only take like maybe a minute to draw. The other one with the construct logo is a bit longer, so we can leave that running at the end and answer some more questions in the meantime.
Okay.
But this was a good demo. I had to in my program I had to scale the image properly, so I had to take the dimensions of the image, the width and the height, and scale it to the board dimensions. And this is actually the smiley face was a good demo because I could see if the circle came out a perfect circle or if it was a bit more like an ellipse, which would tell me that I got my dimensions wrong. But luckily, you'll see it looks like a pretty close to a perfect circle once it's finished drawing that.
And here it's using Cartesian plans
Yeah,
or.
it's using Cartesian, yeah. So
Mhm.
you can actually feed it a lot of coordinates. Initially, I was giving like I was reducing the amount of points that I was feeding it. And then I just decided to give it a bunch of points, and it's actually able to plan and execute without any issues, like
Mhm.
up to like 2,000 points at a time. So yeah, in this way you can use Move It to basically transform any robot arm into a CNC or a 3D printer or whatever you like.
Yeah.
Just be careful when you're doing it. Okay. I think, okay, it's gonna draw it maybe one or two more times, and then we can move on to the next one.
Yeah. Yeah, it's really cool. And we can see also that the arm is quite precise, right? By following the trajectory. So,
Yeah. Yeah, it's surprisingly precise.
Rodrigo is adding some extras there.
Wait, I cannot see it. I need to move the arm out of the way. Let's see if I manage to this uh, trajectory. I need to do a raw service call for this.
Hmm.
Let's see, is it gonna? Oh no, sorry. That is execute trajectory. Then that. Okay, and now I can give it the type of trajectory I wanted to execute. And I just created a bunch of types, and type number 5 is the go to home trajectory.
Any specific reason why you decided to make it a service and not an action, or?
I just thought a service would be easier. I wouldn't have to uh, need to always give feedback, and it's mostly like ask for one service, like ask for one trajectory and get a response. I didn't really see the need for constant feedback from it, but I think it would be a really good idea in the future to give constant feedback. So yeah, we can try the other one.
Yeah, we can at least start it.
Yeah.
You can remove the board from the service also, or?
Oh yes, I should do that.
Hmm.
Yes. So that's number 3. Okay, and I should have, yeah, number 5 will bring it back home.
Yeah, and let's try the construct logo and leave it there running because probably it's going to
Yeah,
take like several minutes to finish, right?
yeah, it's a bit longer.
Yeah, yeah, we can at least leave it there running and see how it starts. That one is a much more complex set of motions, so it's going to be interesting to see it.
Okay, and I need to give it one more parameter for this image. I need to skeletonize it, which basically reduces all the contours. Instead of having like double the contours, it'll try to reduce it to only single contours, but it still makes some duplicates.
Mm.
And I think I also need a step size for this one. I'll give it a step size of 10. And I need to put a dash P. Okay, let's see if that works.
Looks
Okay.
like. Yeah, that looks
Okay,
like
so it's
one of the
starting,
legs, right? Yeah.
yeah, it's starting from the bottom here, the 2 corners of the legs, and it'll make its way up.
Yeah, that's really cool. So something interesting might be to, I don't know, have some easy way to pass images to the robot, right? And ask them to draw them, something like that.
Yeah, I was thinking of doing that with the web interface, be able to like upload an image directly on there,
Mm.
pass it through the ROS bridge to a node that processes and executes it. And what would also be cool is if you could like do an API call to some like large language model, like a ChatGPT or Grok or whatever, to like feed you an image. You just give it a prompt,
Mm-hmm.
and then it responds with some kind of image for you. And then from there, you just directly process that and output it. That would be something
Yeah,
cool to try in the future.
yeah, yeah. So here it's not repeating, right? The
So it is repeating some of
mm.
these features. I think it's because it's trying to generate closed contours. And when it does that, it's like creating a bunch of triangles next to each other, and they're gonna overlap. But at least without the skeleton eyes, it would be drawing like twice as many lines. It would have been repeating everything twice. And from my understanding, skeleton eyes basically like if you have two parallel lines, it tries to take the midpoint. So it kind of creates a skeleton of whatever shape you give it. And for this image, it works pretty well.
It looks really, really cool. I mean, it looks like it has already a good part of the image finished, right? So
Yeah.
yeah, so the idea behind this project basically is to it's in the context of an automated cafeteria, right? Our Starbucks cafeteria. So the idea of this, oh, it disconnected.
Oh no, I forgot to reserve a
No.
session. Well,
Okay. Well, we saw it almost finishing the drawing, so
we saw about half of it,
yeah,
the
yeah,
bottom
yeah.
half.
It's more than enough. Okay,
Yeah.
Roberto. So if you want to say some last words, I think we can leave it here. So thanks a lot for the presentation. Really cool. I hope that everyone has enjoyed the presentation and has learned something from it. I'm sure that you have. So yeah, if you want to say some last words.
Yeah. Thank you very much for joining, and I hope you enjoyed the presentation and the demo. And also thank you very much to Alberto and to the rest of the Construct team for making this possible. Really happy to be able to showcase this, and yeah, thank you very much.
All right. So yeah, then let's leave it here. Thanks one more time to Roberto for his very cool presentation. So yeah, thanks all of you for being here. I see that you have been active in the chat and enjoying the presentation, as I have. So thanks to all of you too. And yeah, so we will see you in the next set of final project presentations, which hopefully are going to be pretty soon. So yeah, until then, as always, keep pushing your robotics learning. Bye bye.